All right, so unit one kinematics, right, where we studied on the study of motion without forces or energy involved. Remember, we call this kind of duck on pond physics. So just be aware that that's all the stuff that we're just worried about the surface. We don't care about forces yet. We don't care about energy yet. And so we focused everything around two types of equations, right? We had something that was what we call a definition equation, and then we had the cake, right? The constant acceleration kinematics equations. The definition equations were such things as change in position is equal to x minus xo, right? That was our displacement. And then then we had velocity was defined as the rate at which position changes, or delta x over delta t. And then acceleration is the rate at which velocity changes, which is delta v over delta t. Also, so we want to kind of what x is position, delta x is okay. V is speed or velocity. And generally, if we want it to be velocity, we'll put that little vector arrow over it, or in textbooks, it's bold-faced. T is time, and A, again, is acceleration. And so you do see the what I just wrote here. You will see this on the AP exam. We'll have like the equations, and then it'll have the what everything means along in the second column. Okay, I did write a D up there. D is distance. Okay, but that was the one thing there. You got the definition equations, which are what really, if you went to the textbook and looked up the definitions, that's what you would see, right? And you can transfer those definitions into equations. Sorry, I'm enjoying my nice insulated cup with tea. Right? That's my old school in Tennessee. We were also the Eagles. All right. Then we had the set of equations that we called CAKE, constant acceleration kinematics equations, right? That's what CAKE stands for. And these are the main equations that we used. So we had V equals V0 plus AT. We had X equals X0 plus V0t plus 1/2 AT squared. Then we had V squared equals VO squared plus 2A delta X. And you can write this one as delta X equals V0t plus 1/2 AT squared, right? And sometimes you would need that kind of relationship to look like that. And then we had the one that is often not given on these type of exams, but you have the one without acceleration, which is just delta X equals 1/2 V plus V0 times delta T. And remember, this 1/2 V plus V0 is just what we call average velocity, okay? And remember that CA means constant acceleration, okay? Remember, in physics 1, we always assume constant acceleration. In physics C, we don't assume constant acceleration. It's given to us in the problems, all right? And so, so a big thing about, again, here in this unit was also graphing. I just want to kind of talk about some of that stuff too. The two main important questions for equations for graphing were the first two. So this is the equation of a VT graph, and this is the equation of a position time graph. And so if there was no acceleration, remember our graphs look like this. In fact, let's change this up a little bit. And so we had PT. If it was no acceleration, meant constant velocity. This was a straight line, or it could be a horizontal line. Remember, horizontal line means rest on a PT graph. And then we had VT graphs. So v, t, these are always going to be horizontal lines if there's no acceleration. And to remember that there is a difference between a horizontal line on a position time graph and a horizontal line on a velocity time graph. Okay. For a velocity time graph to be at rest, it would have to be on the axis. So v would have to be equal to 0. Okay. Now, constant acceleration. Okay. Your VT graph or your PT graph would be parabolic. Okay. Your VT graph, your velocity time graph, would be a horizontal line. And then your acceleration time graph, right, would be a horizontal, sorry, VT graph in constant acceleration would be a slope line. I apologize for that, where the slope of the line, right, is your acceleration. Okay, here on PT graph, the slope of your line would be your velocity. And then acceleration time graph would be just a horizontal line, right? And so those are the different types of, and so what I'm doing is I'm actually recording this so that I can post this as well. I'll make sure that I'll take screenshots of each slide, if you want to say, and make sure those get posted. So these are just going to be like simplified versions of any type of big kind of review packet give you. Right, the main thing is how do we accomplish some of this stuff. Also in Unit 1, we did talk about projectile motion. Right, and so remember we had 2 types of projectile motion. We had what we call a cliff problem. Right, and so you would be given, or you would have to find a horizontal position, which we call range. Okay, and then you also, given a height where your initial velocity would only be in the x direction for these cliff problems. Okay, and I'll give you the projectile motion equations as well here in a second, them simplified. And then the other type we had was when we launched it up at an angle. And so your VO, and you would have a theta, right? Again, you would have a couple things you would have to probably solve for here. Is this range, okay? Maybe this max height. Okay, and so those are the 2 types of projectile motion questions. Now, when you launch it up at an angle, right, this is where you would have to break up your vectors, your initial velocity vector. Right, so this would be step 1, and then step 2, do the rest. And here are your projectile motion equations. And so remember, there's gonna be an x version and a y version. And remember, in the x, there's no acceleration. In the y, the acceleration is that negative 9.81 number, which you can use 10 if they say, unless they say otherwise. Okay. And so what really happens is anything in the x direction, anything with an acceleration would go away. And so that's just telling us that VOX would equal VX. So your initial velocity equals your final velocity. Remember, it's constant velocity in the x direction. And then your position would just simply be VOX T. And I'll write down the VOX equals VO cosine theta. Okay. Now the y direction is where it gets, where you would have to keep everything in it. So you would do VY would equal VOY minus 9.81 T or 10 T. VY squared would be VOY squared minus 19.6 delta X or 20 delta X. And then you would have Y equals Y0 plus V0Y T minus 4.9 T squared. And if you want me to, and I'll highlight the most important ones. So the most important equations in both directions would be, oh, sorry. Wish I had just the highlighted one. But here, I'll just circle them. So the most important ones would be this one and this one. Okay. As long as you know all that information, you will be able to determine everything about that. And really, this is the most important equation. Because if I can write the quadratic, I can find time, I can treat it as a math problem and find the vertex. And so remember, this up here, we call it the y max physics-wise, but it's the vertex of the parabola. Okay, that's made. And over here on the cliff problem, we are starting at the max height. So this actually ends up being our max height already. And so if someone asks me to go down the x side again, remember, x is constant velocity, which is the reason why, you know, ax equals 0, and then the formulas just get simplified. And the formulas are the ones, right? The formulas I'm referred to are these right here. Okay, all the cake equations, right? That's what I'm referring to when I say the formulas, and we simplify them. And so that one would be, you know, we'll just, the x direction is very simple because of the acceleration being 0. And the way it works out is you have a constant velocity, or a ball moving on a table at a constant velocity, and then an object being dropped in free fall. Okay, and so that you combine those two motions together, you get projectile motion. Okay. And so, guys, remember, I will post these pictures up separately, so you don't have to like try to find them, or try to, you know, get this all down. Two things: one, I'm recording this portion, and then I will also make sure that these get screenshotted and posted somewhere as well. Okay, just kind of simplified notes. In fact, I can screenshot this one real quick. All right. All right, so that's all screenshotted. And so I want to keep going forward here. I can save them all. All right, so unit 2, remember, it was Newton's laws. Now, I'm not going to go over all the different scenarios, right? For, you know, we don't have that time right now. Okay, and plus we did plenty with this. So the big thing about Newton's laws, remember, sum of the forces is ma, right? And remember, we had just a bunch of forces. Okay, and the basic steps, right? Problem solving for Newton's laws was draw, sum, solve, right? Draw your FBD, do sum of the forces is equal to F equals, or sum of the forces is M times A, and then just solve for what you're looking for, right? Again, you know, you may start the problem off doing Newton's laws, but then end up, if it's a true dynamics question, you may start doing Newton's laws, and then you end up having to use the motion equations, or vice versa, right? And remember the connecting factor. So if I have kinematics and dynamics, right? Just remember that they're connected by acceleration. So when we talk about dynamics, now we're studying underneath the water, right? We're going under to that, we're going under the water and focusing on now that duck kicking everything and how they getting around the water versus kinematics, which is just kind of sitting on top of the water. And so just remember that. And the acceleration dynamics is the acceleration kinematics and vice versa. Okay, so this right here you can find using the sum of the forces equals m times a, or you can find it using a kinematics equation. All right, and then we kind of break down, we had different forces acting, right? So we had friction force, is mu times the normal force, and I want to say in the majority of the time, Fn equaled the weight, right? We had, which means we had the formula for weight, which is m times g. Again, g is either 9.81, 9.8, right, 10. Okay, and you don't have to worry about a negative sign with this g because it's already been accounted for when you do your free body diagram. And then, then we have the spring force. Oh, sorry. All right, so we have Fs is Kx. K is what we call a force constant. X is the elongation, right? How far it's stretched. But other forces that we talked about in here was tension. And remember, tension comes from the free body diagram, right? It comes from the solving for tension. There's no set formula for it. It comes from free body diagrams. And even we also had the applied force. Also came from free body diagrams, right? Unless it was given to you, okay? And so, like I said, and other things that we, again, we had Atwood machines, right? Where we treated it as a whole system to find acceleration. And then we broke it apart into separate systems to find tension. Right? And I mean, we spent a whole week really focusing on some of this stuff, okay? And then we also did the surfaces, right? We broke down the surfaces, which was very important. But again, the main thing, right? Your problem solving here. Draw, sum, solve, okay? Draw the free body diagram, sum the forces in each direction, and then solve for what you're looking for, okay? Then we moved on to unit 3. And I'm highly recommending that you guys try those assignments I put into AP Classroom, right? Because those are questions that are written by AP test writers and people who, like I said, keep saying they know the exam more than I do. And so I would trust those before any question that I tried to write for you. And that's why I use AP Classroom a lot for a lot of things, okay? So what I mean by tension is found from the free body diagram is that there's no set equation for tension. Like there's no equation that says tension equals this, right? You have to sum the forces and determine accelerations and no acceleration and stuff like that. That's what I mean by tension comes from the free body diagram. And same thing in kind of the long run, same thing with the applied force. The applied force is not given to you and you're asked to find it. It's kind of the same idea. It's going to come through summing of the forces, okay? All right, unit 3 was our UCM adaptation unit. Right? The main formula is gravitation, G over R squared. Remember, an inverse square law, that the force varies inversely to the distance between them. And so remember, this is not a radius, this is between centers. Okay, so it's not like a radius of a circle. It's the distance between those two centers, or the distance between two objects. A lot of times when you talk about this, you look at like universe, all right? So space. And then we also did centrifugal. There was a whole kind of table of equations. So centrifugal force, centrifugal acceleration, and we got speed in circular motion. Okay. But one of the things we do here also is that we oftentimes are like set equations equal to each other. So one of the things we did was we set the, when an object is in orbit, set the potential force m1 m2 over r squared equation equal to each other and solved it. Get this was the International Space Station. Okay, and then we also did, we set mg equal to g m1 m2 over r squared to get an equation for the speed in orbit. Right. Our capital G. Go backwards, wrote these, then input your centripetal acceleration, and then plug in centripetal force. Remember, centripetal literally means center seeking. So remember, the positive direction, so positive is always into the circle. Now the last unit, the one that we just kind of finished with our notes, right? Unit 4 was WEP, work, energy, power, energy. AP just calls it energy. And remember, this is a big portion of your test, right? This is like 16 to 24% of your test. Remember, we talked about open versus closed versus isolated. Here in AP Physics 1, all of our systems are isolated. Okay. This is AP Physics C, so C1. Okay. Then we talked about work, and I'll just give you the F delta X cosine theta, right? And so remember, we're applying a force through a distance, and if the force is at an angle, remember, we want the parallel component. And the thing that we did was, remember, for work to be done, there had to be three things. There had to be a force, there had to be motion or a change in motion, and then there had to be a cause. Remember, that force has to cause that change in motion, right? So those are the three things that have to be present, because on a multiple choice question, they may ask you that. Which situation is there work being done? Which situation is there not work being done? And then we equated, and then we talked about kinetic energy, right? 1/2 mv squared. And then we did the work energy theorem, where work done is equal to the change in kinetic energy, and more specifically is actually the change in all energies. And so this kind of broke down to be F delta X equals 1/2 mv squared minus v initial squared, right? And so that's the work energy theorem. Then we talked about potential energy, and we had two. We had gravitational potential energy, and then we had spring potential energy, which then led us into our discussion on conservation energy, right? And so we talked about total mechanical energy, K plus UG plus US. Remember, it's the sum of all the energies. And the conservation energy just tells us that the total energy before equals the total energy after. In fact, let me write before and after. All right, and so that formula actually gets kind of ugly. K initial plus UG initial plus US initial equals K final plus UG final plus US final. But remember, even though it's kind of ugly there, things get canceled out based on situations. Like, so for example, if we have a roller coaster, we don't have a spring, right? It would be cool to watch a spring do all this, but it doesn't. Okay, if we have no change in height, well, we have no potential energy, right? And so the key thing about conservation energy problems is setting that that low point. Okay, where is that H equals 0 point? Because then that allows you to cancel out potential energy somewhere along the way. And that's pretty much all the equations that we've done up until this point. And this is a very quick, brief overview. We spent, 30-something weeks on these 4 units. Okay, so I shouldn't have to dive too much into this. And you have access to the Google site. It has all the videos. You have the AP classroom assignments to try. So what I'm going to do now Yeah, sorry if it looks messy. It's kx in the equation. So this, right, is a k.
Mr. Londa, the line right above
Right.
that.
So what I will do is um,